Hello and welcome back. In this video, we are going to look at batch normalization in TensorFlow, and there is also an alternative method which is batch norm with global normalization. However, this method has been deprecated, so we won't be discussing this method. We'll just focus on the batch normalization. And before we get into the code, I just wanted to point out uh, this reference that is cited Ioffe et al. And if you look at the paper, you can see that uh, they talk about the phenomenon of internal covariate shift, and that's where this type of normalization method would be more useful. Now, the what my understanding of internal covariate shift here is that the distribution of the inputs to each layer of the neural network changes as the neural network trains, and this can become an issue for deep neural networks. Uh, and this can also then slow down your training and make the network harder to learn effectively. What this method does is essentially, this is what we know of. So if you just ignore the gamma and the beta part, we know that the normalization step has your value minus the mean divided by standard deviation. So in addition to that, we are multiplying this value by gamma and then adding offset or shift, which is beta. And so I've put the description here. You could pause the video and read through this. Scale essentially does the job of sort of amplifying the values, and the offset just shifts the data. And I'll show some visualizations, a simple plot to show what these two actually do. Now, getting into the actual code, I've already written the code, and here it is. So let's say we have a input data, and the input data is just this tensor. We run this, and we can look at the tensor, or I can just simply print it here. Print input underscore data. So that's the input data we have. My mistake, missed the T. Input, that's the input data we have, which is a tensor. And let's say this is a tensor for the mean values we have calculated, and this is the tensor for the variance that we have calculated. And if you remember, here this says standard deviation, but we are creating a tensor for variance and not standard deviation, but we'll do the square root to get the standard deviation, because if you probably already know, standard deviation is square root of variance. Next, we have these two values, scale and offset. So these again are tensors, and the values in these tensors are just arbitrary values. And we also need to specify epsilon, which is to avoid division by zero errors. So the epsilon isn't written here, but if you go into the paper, let's say here they specify, you see, equation 11 in algorithm 2. So that's what this is coming from. And if you scroll down, this should be the algorithm. Yep. So this is the algorithm 2, and this is the equation 11. And so inside of the square root, we are simply going to add the epsilon value to the variance term. Now getting back to the code, here is how we could input the values to batch normalization, and this is the same as what is described here in the docs. We have the x, mean, variance, offset, scale, variance epsilon, and name. So those are the values we have. For x, we put the input data, the tensor we created above, and then we put the all other tensors for mean, variance, offset, and scale, and of course the value for variance epsilon. Now when we run this, we get this output tensor which is now normalized. And just to make sure how this calculation works, let's say we'll try to calculate this value of minus 0.399, and for that here is the, I've already done these calculations. I'll just walk through these here. That's the tensor we have, and I could run that again just to be sure. Input data. All right, so this is the tensor we have, and if you look at the formula that we had, which was we essentially multiply by the gamma. So this is our gamma 0.5, and that's 0.5 because um, here we have this scale which is the gamma for 0.5, and then we have the offset or shift which is 0.1. That would be our beta, and that's what we have. So plus beta is here and the gamma is here. All right, next is the x value. So let's for now say that we are taking just the first value. So we have the 1 that goes right here, and minus the mean. Why minus the mean? Because we are sort of doing the zero mean of the data, and that's what we are doing here, x minus mean. And so we now subtract the mean from that value, then divide it by square root. So I've put this power here. This is for the square root, and this is 1 plus epsilon, variance epsilon. So 1 is the variance. If you come down here, that's the variance, and that's the mean value we have, and here is the variance epsilon. When we put these value in place and run this cell, we see that we get the same output as what we had up above here. So that's how we can calculate the value for the batch normalization using this method, which takes into account the internal covariate shift. So that's what this would uh, take into account. Now, what does the scale or scale and shift actual do? So you're probably wondering, it's good that this is there, but why would I care about using the scale and shift parameters? Why wouldn't I just go ahead and use the x minus mean divided by the square root of variance or sigma? Why add these scale and shift parameters? And the reason for that may become evident in this example. So what I'm doing here is I've created another data which is just array right here, and we calculate the mean and variance for these. So let me go ahead and print these values as well. So print x, and I'm just going to print an empty line after that, and after that let's also print the mean value. So let me go ahead and say mean. So that's the mean value, and then we also have the variance, and let's put the variance here, and let me go ahead and run this. Before we go to the plots, let's look at the value. So that's the mean value of the first column, mean value of the second column. So that's uh, 5 plus 3 is 8 plus 1 is 9 divided by 3 is 3. And that's the variance for the first column, that's the variance for the second column. Now here is the value for epsilon. That's just to avoid division by zero errors, which is a small value close to 0. Now we are going to calculate the normalized values using both of these methods, which is without using the scaling and with using the scaling. So here is the first method. Now here we have x minus mean divided by square root of variance. Epsilon is just there to avoid division by zero errors, and we'll use that here. Next, here we have defined scale and shift. So now what we'll do is we'll take the normalized values that we had calculated above, and then just amplified, multiplied by a scaling value, and then add a shift. So we are just uh, sort of amplifying the value and then moving it uh, on this on in some direction, and then we create these plots. We have 3 plots, as you'll see. uh, so the very first plot shows us the original data, where we have the x-axis, which is feature 1, y-axis is the feature 2, and we have these data points. The first point is at 1 2, and that's because we have the value of 1 in column 1, which is feature 1, value a of 2 in column 2, which is feature 2, and so on for the other 2 points. Now when we perform the normalization, we get the values in a smaller range between it's not between -1 and +1, but they are pretty close to that value, as you can see here. So the very first point has now come down here, and the second point. So the largest value in feature 1 in original data had a value of 6, but now the value in after normalization is close to 1. What happens if we use the scale shift? So here is what we have with the scale shift. The values are within the normalized range, but then we have shifted it and we have amplified it, and so these are the values we get. Um, the first point, which was originally at 1 2, is now at -2, and a value slightly under -2.5. And here are the actual values. So normalized, no scale shift. This is the value we have, -1.22. And if we multiply it by the amplifying value and then add the shift, then we get the value of -1.949, and that's probably this value right here that we see, uh, -1.9. I'm imagining that's the value, because here is the data with the scale shift, right? So that's the value, -1.9, very close to 2, -2, and then we have -2.3. So that's that data point, these two values. So again, then the question again we can ask is, why use the Sergey method versus the original method? Does it have any advantages? We talked about this earlier, that it can help in convergence. So do we want to see it in action? Yes. So what we have here is an example where we have a generated data set, and this data set has 2 features. So the X train has 2 columns, and we have 100 values in each of the columns. And Y train we have just 100 values. And here are some of the values. Top 2 values, not I mean the first 2 values that are here in the X train, and you can see that the maximum value in the first feature, that is the first column in X train, is 238, as compared to 2.2 in the second column or the second feature. So the values in extreme are significant, are much larger magnitude as compared to the other columns, so 100 times larger. So how would the normalization based on the scale and shift help? And for that, what we have here, let me zoom out a little bit so you can see. So what we have here is a model that we are using Keras at this point, sequential model from Keras. We have put this in a function, build model, and use scale shift is just going to bring some true or false value that we use in this layer. Bash normalization center is equal to use scale shift. So if it is true, it will do the centering. If it's false, it won't do the centering. So that's what we have, scale shift if true. And the layers, other layers. So that's the input layer. We have two neurons because we just have two features. Then we have the dense layer, inner layer, one hidden layer with 32 neurons and ReLU activation. And the batch normalization would have the same 32 inputs from the previous layer for normalizing. And then the output layer is again a dense layer with just one neuron with a sigmoid activation. Here we have a function with the lines of code that will call the build model function to build the model, then compile it, and then fit it to the train data. So X train and Y train. So let's run this. And now, once that is done, we can now call the train model with a true and false. So what we might mean by that is without scale shift, so we have that false, and if we specify as true, we say that we are going to use the scale shift. And so after we run that, we get the returned history. We put the history, we use that history loss to create some plots. And here is a plot with two values so this is the blue line is no scale shift and the orange line is with scale shift. And as you can see, if we even run this again, we see that the orange line with scale shift is always lower than the blue line. It is below that line. So that's just telling us that um, it uh, it it is helping in reducing the loss at a faster rate or even a lower value as compared to without the scale shift. Uh, Now next let's look at the batch size, right? So how would the batch size work? And for that what we have here is I've created a batch size of 32, and let's say the number of features is 10. We have three and we are creating three batches. So here is the synthetic data that we are creating for X batches and Y batches. So let's run that. And then if when we perform the training on this, what we can do is we can specify the value of batch size when we perform the fit. So here we are saying batch size is equal to batch size, which is in fact 32. And the data that we are going to input here is this concatenated data. So what it'll do is it'll take chunks of data from there. So 32 records and uh, train the model sequentially on these batches. And then here is the evaluation based on some random test data that is created. So let me go ahead and set the random seed. So if you run this, maybe you'll see the same values. np.random.seed 0 on this, and these are the values that I get, which is 0.59. What's more important here is to notice that the fit is able to take the data in batches from the X-train to perform training. On the other hand, if we were to use the entire data set, such as here, so this is essentially saying that batch size 32 multiplied by 3, so that's essentially saying 32 multiplied by 3, that's 6, so that's almost all of the data, 96 records. And what, so let's leave it at that. And when we run this, in this case, it is using the entire data set for training as opposed to here, which is a smaller batch size. Here the batch size is almost the entire data, not exactly, but almost 96 versus 100. So that was That was it for this video. I hope in this video you got an idea of how the batch normalization is done. Then uh, so we talked about how what the batch normalization is. Then we talked about what does the scale shift actually do. Then we looked at when to use this method as compared to the original method. We looked at batch size, and then we looked at how we can use the batch size as an input when performing the training. Uh, if you have any questions, comments, or suggestions, please do let me know in the comments section below. I hope this was a useful discussion for you, and hope to see you all in the next video as well. Thank you.